Hello, in this video I'd like to ask and partially answer the question, is there some function whose graphs in Cartesian and polar coordinates coincide? That is, if you graph y equals f of x and r equals f of theta on a graphing calculator, you'll get the same graph. This is a very fun problem, and I encourage you to pause the video now and try to see what you can figure out on your own. See if you can figure out some properties that the function f of x must have, or see if you can find some function that's pretty close to a solution to this problem. I've put together an interactive to go along with this video, and you can try out and compare the graphs of y equals f of x and r equals f of theta for whatever functions you want. This interactive uses the Desmos API, so you might find it convenient to use the function domain restriction feature. Here I've restricted the domain of our function to be between 0 and pi over 2, so that when we plot the polar graph, it doesn't wrap around. Because of course the Cartesian graph isn't going to wrap around. I've only been able to come up with a partial solution to this problem, so I encourage you when this video is over to see if you can find your own techniques for solving this problem. So to start off with, suppose that we know a particular point on the graph. This tells us that f of a is equal to b, because this point is on the graph of our function in Cartesian coordinates. But now that we know this fact, we can use it and the fact that this is also the graph of r equals f of theta to conclude that the point with r equals b and theta equals a is also on the graph. Writing this point in Cartesian coordinates, we get b cosine a, b sine a. So given that this point here is on the graph, this point here also has to be on the graph. And because sine a is always between -1 and 1, this point here is always going to be closer to the x-axis than our original point. And so I'm going to call it the lowering of this point here. However, this gives us another point on the graph. And so we can consider the lowering of that point. And that point also has to be on the graph. And the lowering of that point has to be on the graph, and so on and so forth. We have an infinite sequence of points that has to be on the graph. And similarly, we can do the reverse. If we know, for instance, that this point is on the graph, this point here with polar coordinates, AB, is on the graph, then we know that the point with Cartesian coordinates, AB, has to be on the graph, because both of them are equivalent expressions of f of a is equal to b. So we know that if the lowering of a point is on the graph, then the point itself has to be on the graph. And we can actually keep going in the reverse direction. Knowing that AB is on the graph, we can interpret this point here in polar coordinates. The polar coordinates of this point here, r is equal to the square root of a squared plus b squared, and theta is equal to the arctan of b over a. We have to make a few assumptions about a and b in order for this equation here to hold, but I haven't been able to find any solutions that use other branches of the arctan function. And because we know that this point here in polar coordinates is on the graph, then this point here in Cartesian coordinates also has to be on the graph. I'm going to call it the raising because it's always above the original point. So it might be somewhere over here. And then this point here has a raising itself. And then this point here has a raising itself, and so on and so forth, giving us an infinite sequence of points that stretches out in both directions. And because the processes of arriving at the raising and lowering of various points were inverses to each other, the raising of the lowering is the original point, and the lowering of the raising is the original point. So we only get this one bidirectionally infinite set of points that we know have to be on the graph. This interactive allows you to visualize a point and its lowering by clicking this button here. Here you can move this base point around, and it will show you where the lowering of that point is. Notice that when the base point is on the Cartesian graph, the lowering is on the polar graph, and nearly vice versa, but not quite. By pressing this button, we can show the raising of the point as well, and notice that when the original point is on the polar graph, the raising is on the Cartesian graph, and nearly vice versa, but again, not quite. This interactive also allows you to visualize the entire sequence of raisings and lowerings for a particular point. Of course, it's only going to show you some finite subset of that, but you can watch as we move this point around and see what happens to the sequence. It seems like there's some nice, almost parabola-shaped curve that if we stick along, the points kind of follow that curve. And then when we diverge from that nice curve, the points start wobbling. They start diverging from each other. And we can see that when the points leave the first quadrant, then lots of weird things wind up happening. So we probably want to stick to the first quadrant. It's worth noting that this sequence of points actually creates a graph that satisfies the conditions that we're looking for. This gives us the graph of a function with a very discrete domain, such that the graph of the function in Cartesian and polar coordinates is the same. It satisfies this key property that makes that happen, that if a point is on the graph, then its raising is on the graph and its lowering is on the graph. And that's all we need to have a graph that's the same in Cartesian and polar coordinates. Of course, we need to make sure that we actually have the graph of a function here, but for most points, we're not going to wind up having points being directly above or directly below other points in the sequence. We just need to wiggle the base point around a little bit to make sure that that happens. But this is kind of a disappointing solution. I'm not interested in solutions that wind up looking something like this. I want to know what the equation of this nice smooth curve that we're seeing is. In order to get started figuring out what that function is, I'm going to want to get these points to line up as closely as possible to the ideal solution. So in order to avoid situations where the graph kind of diverges or zigzags, as we see here, I'm going to want to take the angles between consecutive points and measure how far they are from being collinear. I'll take that difference and I'll square it and I'll sum up over all of the points that we have available in our model, and that'll give us our overall angle badness for our model. Notice that this angle badness value gets larger and larger as we diverge further and further from our ideal curve, and as we get closer and closer to our ideal curve, the angle badness value gets smaller and smaller. Of course, we can't get this badness value to be equal to 0 because there's necessarily going to be some amount of curving to this curve. It's not going to be a perfectly straight line, but we can get this angle badness value to be really small. Now, I don't consider myself to be much of an optimizer, so I'm going to use a very basic algorithm to find a starting point that minimizes the overall angle badness. Specifically, I'm going to take our base point and I'm going to add a random vector to it. If that new starting point has a lower angle badness, then I'm going to keep it. And if it doesn't, I'm going to go back to the original point. And then I'll continue this process of adding a random vector to our point until the angle badness is as small as I'd like it to be. You can watch this process in the interactive here. Once the optimization starts to slow down, you can reduce the step size in order to fine-tune your solution. So this gives us a sequence of points that's a very good approximation for our ideal smooth curve. And I've included here a dataset that you can download as a CSV file if you want to plug into your favorite data analysis software. But I've also rigged it so you can do regression directly in the interactive. Use this input here in order to set up some parameters that you can use in your definition of f of x. And then the interactive will randomly modify that parameter in order to get the curve to agree as closely as possible to the data points. In order to refine this process, we'd like to start off with more than one base point. This interactive allows you to increase the number of base points to increase the density of the overall curve. We see here kind of a wobbly but nonetheless smooth-looking solution. It may be the case that there are multiple smooth curve solutions to this problem, with some of them more wobbly than others. And in fact, it seems like up to a certain point, we can specify an arbitrary behavior of our base points, and then this will just copy into the raisings and lowerings of that versions of that arbitrary smooth behavior that we've specified, as long as our starting arbitrary smooth behavior satisfies certain inequalities. For instance, we'd always like a raising of a point on our curve to be to the right of the original point, and we'd also like the lowering of any point on our curve to be to the left of that point. And so all of the points on the curve are going to have to satisfy these inequalities here. If we're viewing these just as constraints on our base points, we also want it to be the case that the successive raisings of our base points and the successive lowerings of our base points also satisfy these inequalities. This gives us an infinite collection of inequalities, and we can plot. It's more helpful to plot the regions where these inequalities don't hold, which we can do with this button here. And we can see that there's a nice region in between where our base points are allowed to be. If we have just one base point, we can see as we get closer to the edges of this region, points get closer and closer to being directly above each other. And in the middle of the safe region is kind of the nice smooth curve that we're looking for. It's not enough for our base points to just be within this region. There are some other inequalities that they have to satisfy as well. For instance, the points t, f of t are going to trace out the curve from left to right and bottom to top. This is a parameterization of our curve. As such, the raisings of those points must also trace out the curve from left to right and bottom to top. And we have this formula here for those raisings. In order for these points to go from left to right as t increases, that means that arctan of f of t over t must be increasing in t. In other words, its derivative with respect to t must be positive. And when we calculate that derivative and solve the corresponding inequality, we wind up getting that the derivative of our function has to be at least f of t over t. So in addition to having to make sure that our points are within this nice safe region, we also have to make sure, for instance, that the slope is sufficiently large to make this inequality hold. We can see that by making our points have a low enough slope between them. The points above them wind up going backwards. And if we were trying to smoothly connect these points, that would cause the curve to go backwards and not be a function. So there are other constraints as well. This isn't all of them. You can calculate more constraints that have to be satisfied. But within these sets of constraints, we can specify arbitrary behavior for our base points of our function. We can trace out an arbitrary curve that satisfies these constraints and copy the curve to its raisings and lowerings, and that will give us an arbitrary curve that could be as smooth as we want, that gives us a solution to this problem. But of course, that's really not what I want. I want to know what this nice smooth curve is. So I've also included a piece in this interactive that will wiggle around the several base points in order to try to minimize the total squared distance between all of these points. Again, this gives us a data set that we can plug into our favorite data analysis program, and I was able to use this to find a highly accurate approximate solution. which we can see here. Of course, these extra curves are from bits of the domain that we're not interested in. And notice that we have to zoom in really closely in order to see the difference between our polar and Cartesian curves. So thanks for watching. This project was a ton of fun to put together, and I hope that some of you know some numerical approximation and data analysis techniques that I haven't been able to make use of for this problem that can shed more insight into it. I'm looking forward to seeing what you're able to discover in the comments down below. So thanks for watching, and be kind to each other.